All right, fantastic. Good morning, everybody. So I am Brad Generu. I'm the Global Lead for Healthcare Alliances here at NVIDIA. We're holding Digital Health Developer Day. So for the next 2 hours, we have a great set of speakers lined up, a lot of content. We're going to be talking about all the SDKs and technologies that help enable all of the developments that you're building to transform the world of healthcare. Our first hour, we're going to talk a little bit about the technologies that NVIDIA brings. I'm going to talk a little bit about the healthcare perspective of the technologies. And then I've got experts lined up. We have Arun and Adi who will cover the reasoning side, the language, the speech side, as well as inference at scale. So strap in. We're going to go through all these technologies. It's going to be great. I'm covering my colleague Raghav Bani. If you saw him on the program, he was unable to make it this morning. So you get me. So let's talk about healthcare and some of the challenges that we're facing today. It's been pretty incredible watching the different breakthroughs that's happened, but all of these things are so necessary because when we think about what's happening in healthcare, where we have an aging patient population, we have populations around the world that do not have access to healthcare. We have burnout happening on the physician side, on the nursing side, that's unprecedented. If you think about the number of hours that our clinicians have to work to catch up on everything that's happening during the day, it's pretty incredible. And we're seeing that most hospitals are struggling to even make it from a financial perspective. We need to do more with less, and that's just a reality of it. And I mean, the great news is technology has been racing forward across all industries. And what we're seeing with the breakthroughs on large language models, healthcare has been a benefactor in a way that technologies before have not. We're seeing these transformations happen from the core, from the EMR, from the systems, all the way forward to meeting the patients where they're at in their journeys. If we just take a look at where we've been and where we're going, back in the early AI as a concept has been around for more than 60 years. We celebrated 60 years last year for what artificial intelligence is. But it was really breakthroughs that happened around the early 2010s, the late 2000s of the decade, when we started to look at how we could unlock compute to meet challenges around things like computer vision. It started with, can we identify a dog or a cat in a picture? But all the way through to, can we extrapolate that and say, can we identify a stroke or a cancer in a picture, in a medical image? We had this rise of computer vision. Then with transformer models, we saw the rise of large language models and transforming the way that we look at language. And this is where generative AI got its start, where we had the rise of ChatGPT. We then saw a breakthrough in it started with tool calling, this idea of agentic AI. So being able to call upon our services, trigger workflows, interact with those workflows, transform the way that we do things across all industries. But we saw this particularly in healthcare. And we started to look at what kind of workflows can we interact with our clinicians and meet them where they're at, provide them their insights, but also help them in the work that they're doing. The next wave, and you heard about this all throughout GTC this year, is physical AI. If we look at what does it mean for a hospital to become a robot onto itself? Can we use computer vision and large language models and tool calling to transform the entire experience? And we're seeing this happen before our eyes. You've probably heard this, AI is a 5-layer cake. We look at the technologies from, right from what powers our data centers to the chips, whether that's the GPU, the CPU, the DPU. to the infrastructure that connects those together with our data, our storage, our networking, our communication, to the foundational models, and to the applications that run on top of that. And that's no different than what we see in healthcare and how we stack our applications, leveraging these components into building the applications of the future. When we think about across the entire landscape in healthcare and life sciences and beyond, there are many different areas that we could focus in on. I cover digital health, and so we've got our health agents, we've got our inference at scale, but we also have pretty phenomenal technologies in the genomic space, in the drug discovery space, in the medical imaging space. There's many different technologies to unlock it, and if you have a look at just some of the technologies like Monai, like Parabricks, like BioNeMo, these are the technologies that help unlock everything that's happening in the healthcare and life sciences space. In digital health, this whole movement around agentic care allows us to unlock patient engagement. We've got great partners who are meeting the patients where they're at to connect with them. On Tuesday, we had this great panel of speakers that included Maven Health and Sword Health, Maven Clinic, that covered things like women's care, fertility care, mental health, and physiotherapy. Being able to connect with the patients themselves and enable them and unlock their journeys so that they can get the most out of their healthcare systems. Later today, we'll have RAD AI as well as a bridge that will help us talk about improving the clinician experience. When we think about radiologists or ER docs, surgeons, those who are documenting the patient-physician conversation, or documenting what we see in medical images, technologies that help improve the clinician experience will help them reduce burnout. We can also optimize what's happening in the back office, in our health records departments, being able to help on the coding side, on the billing side. And we can extend this all the way through to clinical trials and working with our pharma partners to be able to match our patients with dire, rare conditions with the clinical trials that just might save their life. Building these systems are complex, and this is where NVIDIA comes in to help the entire developer ecosystem with technologies that get them there faster, that get them there from an enterprise perspective, being able to build on top of this. So this is using SDKs and APIs that help reduce the architectural complexity, to make it scalable, reusable, always driving the performance, in many cases 5x or 10x what's available out in the open source space, but also taking in this, being safe, leveraging guardrails to help unlock this. So we have these libraries that meet our developers where they need them best so that they could do their life's work. I won't go through the technologies because we've got, like I said, a great set of speakers lined up, but some of the things that we use is Nemotron, Nemo, Dynamo, and Triton for driving the language, the reasoning, and the inference at scale. We also have voice and speech with Nemotron Speech. Up on our website, you have all the information, the documentation to help drive that knowledge, to be able to take these things and connect them into the workflows that you're building to augment them and drive them at scale. When we think about how agents work, it really comes down to 3 steps, which is perceiving the world around us. So this is using signal processing. This is using keyboard inputs for chat experiences. It's using voice to be able to capture what someone is saying. It's using video feeds to capture what's happening in the room. It's using language to catch sentiment and so much more that we can get from perceiving the world around us. We then use our agents to reason over that, to take all those inputs, to take the knowledge that it has, the database that it has connectivity to, and really think about what is it trying to solve for. Come up with a plan, and then drive action from that, whether that's calling upon other APIs, or trigger workflows, or connect back with a response to the user, whether that's the patient, the physician, the nurse, or other. These agents could be strung together. So you might have your pharmacist, your physician, your nurse, your health records, your unit coordinators, your informatics teams, all connected using agents that work together harmoniously. The way that we stack these make it really straightforward for us to be able to leverage this kind of cross-departmental interdisciplinary workflows, which is really, really important. We can hang these together in what are called blueprints. So in this blueprint, which is a little bit hard to see on the screen, but essentially this is an end-to-end conversational workflow that could start from our Toy Jensen physician to doing the speech to text, to connecting with agents with knowledge across different areas, such as writing doctor's notes or driving intake workflows or being able to navigate creating appointments for our patients, connecting into the databases with Nemo Retriever, connecting with our guardrails applications, connecting with our knowledge bases, and things like drug formularies and appointment schedules, driving the responses back, creating that text to speech, and then providing that response back out to our user in under a second is really the ability for us to drive these conversations. If you want to learn more about what we're doing in the digital health space, if you want to have one-pager access to all the different tools, all the different success stories, the programs that we offer, you could join our digital health developers program, so developer.nvidia.com/digital health developers. A great place to get started. But with the experts here, drop us questions. We're always happy to have conversations. With that, I will pass it off to Arun, who will walk us through reasoning LLMs. Arun, come on up. Thank you so much, everybody. Here you go.
Hello, everyone. Great to be here. I'm a group product manager at NVIDIA, responsible for LLM inference. I'll go into more detail on specifically 2 topics. What are the models we have when it comes to LLMs, and what is the inference stack that we have, and how can you take advantage of it? All right. So the first thing to note is that this is version 3 of Nemotron. We released version 1, version 2, and now we are at version 3. And you might have heard Jensen say this: we will keep releasing Nemotron as long as we shall live. What does this mean for you? If you are looking to build on top of a model that is going to keep improving over time, both from an accuracy as well as a performance point of view, Nemotron is a great model to build on. It is completely open, and we are committed to keep building on it and keep improving it. And the way it's set up today is, for version 3, we have 3 different model sizes: Nano, Super, and Ultra. Nano is a 30B model intended for very targeted tasks. If you're looking to get the model working for a very specific thing, you could use the Nano. Super is intended, 120B is intended for multi-agent systems, and the Ultra 500B is intended for essentially a replacement for frontier models, something that can think, make a plan, and orchestrate a whole agentic system. The key innovations in the Nemotron 3 model family are this now uses a hybrid MOE architecture, which significantly improves efficiency, as well as significantly increases the context length has been increased by about 7x from the previous generation to now. So it has a 1 million context length, which means that for pretty much most workflows, you could just provide the entire context to the model, and it should be able to take it and provide you the response that you need. In addition to the model, Nemotron, you can think of it as an ecosystem that comes with the data and the tooling that you would need if you wanted to customize and build your own version of Nemotron. When it comes to data sets, we have the full suite of things. I'll go into it in more detail, as well as we have tooling called NemoGym that allows you to create your own reinforcement learning environments to tune the model. And we've also published full research on what is under the hood for each of these models. Here's a couple of slides, just taking a quick look at how does Nemotron compare to the rest of the open models in the ecosystem. The x-axis here is the intelligence index. It's a combination of benchmarks from artificial intelligence. it's an average of various different benchmarks showing how intelligent a model is. And the y-axis here is the openness index. How open is the model? How easy is it going to be for you to take the model and fine-tune it if you want it? How easy for you to trace it back and understand what is the data that's been used to train this model? And you can see that Nemotron 3 Super is on the upper right. This is a great thing. And in terms of intelligence especially, it is much better than most other models available out there. Here's another view. Here it is intelligence versus efficiency. The y-axis here is intelligence, and the x-axis is efficiency. And you can see that the top two models when it comes to intelligence are the Nemotron 3 Super 120B and the QN3 122B, 3.5 122B. But the Nemotron 3 Super is much more efficient. So if you're looking to take advantage of the compute that you have and generate more tokens, Nemotron 3 Super is going to be a much better choice at this point. Again, a quick summary of what all you get with Nemotron 3. It's a hybrid MOE architecture, about 4x improvement from the previous architecture in terms of the overall efficiency. We also included by default a technique called multi-token prediction, so that during inference time, it predicts three times the number of tokens and is able to automatically select the right token that is going to help improve the overall latency and throughput. Context length improved by about 7x. And using our Nemo RL Gym tooling, we are able to also improve the intelligence with reinforcement learning by about 2x. So this is upcoming. The Nemotron 3 Ultra is expected to come in about 2-3 months, and we're already seeing that the accuracy results are, for its model class size, it is the best available open model out there. So we're incredibly excited for it. In about 2 to 3 months, you should see the Nemotron 3 Ultra released, and you should be able to use it for applications that require a lot more complex thinking, and this is a replacement potentially for frontier models. A quick slide on everything that we've released with data. So far, we spoke about what is available as a model and what you can use out of the box. But you can also create your own version of Nemotron, and we have various partners that have been able to go this route, take the data that we have, add in their own custom data, and create versions of Nemotron that really work for their enterprise applications. Just a quick look at the various different kinds of data that we've released includes pre-training data, post-training data, including reinforcement learning, supervised fine-tuning data, as well as data for safety and for creating, or how we created Nemotron to work for various different demographics and personas across geographies. So you have the model architecture, the model is available, and you have the tooling to improve the accuracy. There is the reinforcement learning tooling, NemoRL, as well as the Nemo framework if you wanted to train the model. There are techniques that are available to improve the efficiency of the model. This includes things like neural architecture search that you can use to distill the model. You can train a model, you can distill it to make it smaller to fit your very specific use case. We also have a feature called thinking budget that allows you at runtime to restrict the number of thinking tokens that need to be generated. Let's say you are an application and you have a very strict latency constraint. You need the response to come out within, say, less than a second. In those cases, you can restrict the thinking budget to, say, 1,000 tokens, 2,000 tokens, so that as soon as the model hits the token budget, it is going to start producing a response, so that you are always meeting your latency budget. And we also provide various different quantization techniques and tooling for that, so that you can take a model that is in BF16 and you can create FP8 or NVFP4 versions of it that is going to improve the overall latency and throughput. And lastly, recipes for doing each of these step by step. How do you train the model? How do you fine tune a model? How do you make it more efficient with quantization? Everything is available as a recipe that you can take and customize and build things yourself. That was a quick look at what is available from a model and customization point of view. Next, we'll go into LLM inference and what does NVIDIA provide to help you serve models. This can be used for Nemotron. It can also be used for any open model out there. So I'll start with NIM here, NVIDIA Inference Microservices. And what we do with NIM is simple. So a new model gets released, an open model, either from NVIDIA or from the community, any open model. We take the model, and we take all possible optimizations, both from the community as well as from NVIDIA, and we build a container that includes all of those optimizations. We validate that from a functional point of view, from a performance point of view, that this works great. And we make sure that it is secure. We validate that there are no vulnerabilities, no critical or high vulnerabilities. We package it all together and provide you a container. We also provide other Kubernetes support, including Helm charts, K-serve deployment recipes, NIM operator, etc., so that you have everything that you need to take this and deploy it wherever you want. The great thing is that because it's packaged as a Docker container with Kubernetes native support, you can really deploy it anywhere. It can be on-prem, it can be on AWS, or it can be on any cloud that you want it to deploy on, and you can also move from one place to another if you decide to choose a different infrastructure later. And here's what the advantage that NIM provides, and what are we doing internally. So there are a whole set of things that you would need to do when you have to do inference. So there is a model that's available. You have to choose what is the right backend to use, what are the right techniques to use for optimization, do the validation, make sure that you are able to track metrics properly, make sure that Kubernetes deployment is set up properly, and then also make sure that you are able to keep doing this on a monthly basis. Just to look at the complexity here, let's say you are validating 10 different models. There are 10 models. There are at least 3 to 4 different inference backends. There are a variety of inference techniques. There are a variety of hardware. So if you just multiply them, there is a lot of different experimentation that you would need to do to make sure on a month-to-month basis to make sure that your inference deployment is set up to get the best possible efficiency. And that is all the complexity that the NVIDIA NIM factory is taking care of and making sure that it's delivering you a NIM that you can just take and deploy. Just a quick look at what is coming. So so far we've had the NIM 1.0 stack, and at this GTC we announced that we are releasing the NIM 2.0 stack. This is now a single backend container that is going to more transparently expose the underlying inference backend capabilities. So we've had many partners ask us, hey, this feature is available in VLLM. Will this be available in NIM? Now it will be, because you're going to transparently be able to see what version of VLLM is included in the NIM, and all of the features that are supported there are going to be supported in NIM. Same for other backends like TRTLM, SGLang, etc. So the bottom line here is that the features, perf, security patches, everything you're going to be able to get faster. As soon as something is available in open source, it's going to get packaged up, and you're going to get in a secure manner as a NIM container. That was the first major announcement. The second announcement is we're also now starting to support distributed inference. Previously, NIM was a single container, but now going forward, we also have what's called as NIMD, and I'll go into this in the next slide. Also supports various different distributed inferencing capabilities that allow you to take advantage when you're deploying of optimizations possible when you're deploying at scale. So what we are seeing with our partners is that last year people were deploying LLMs for various different applications, and this year people are really scaling it up to hundreds of GPUs, hundreds of nodes. And when you do that, there is a lot of opportunity for further optimization. These are some examples of things that you could do. So for example, let's say there is an incoming request coming in, and it is going to a particular GPU. By default, when the next request comes in, it is going to go to a different GPU, even if there is a lot of commonality between request 1 and request 2. But if you are able to intelligently route request 2 to the same GPU that previously processed request 1, you don't need to recompute the KV cache. So that is going to significantly save you the compute in terms of and reduce your overall latency and throughput. That's one example. The another example is disaggregated serving, where you can split up the LLM workflow into a prefill part and the generation part, so that you process the context in one GPU and do the decoding in a different GPU. This allows you to more flexibility control the latency and throughput. There is also the KV block management, where if you are in a situation where you're running a really long-running agent and there are a lot of recurring computations that are coming in, you are able to save the computed KV cache into other layers of memory so that you're able to reuse it instead of computing it over and over again. So a variety of techniques, we see that for each of these techniques, it results in orders of magnitude improvement. With disaggregated serving, we've seen cases where you get about 3 to 4x. With KV, we're routing about 2 to 3x, and KV block management another 3 to 4x. So it all compounds together, and we're really excited that all of these capabilities are now also going to come to NIM in a packaged manner so that you can take it and deploy it. So this is what the NIMD looks like. You take all of these distributed inference capabilities and make it enterprise ready. So provide enterprise support, make sure that there are no CVEs, and make sure that it is working on the hardware and models that you care about. This is a quick example that was released this week for Nemotron 3 Super that I was mentioning earlier. Just enabling the KV-aware routing immediately improves the time to force token by 2x. So just round-robin routing, you get x TDFT, and with the KV-aware routing, it reduces by about 2x. That was a quick overview of the LLM models and inferencing. I'll now hand it over to Ati. Thank you.
Thank you, everyone. And thank you, Brad. So I hope all of you watched the keynote. And in the keynote, there were a lot of voice-based demos. One of them was the in-cabin, when they were driving and the car was speaking to them. So it's also a start for edge deployment of speech. We also saw the open models, Nemotron voice chat. I'll be speaking more about that. And also we had the machinery and Olaf, Disney's Olaf. He was speaking for the first time. Last year, the bot was beeping. So it's really an exciting year, and we really see that speech is maturing. And it's now being unlocked by multiple verticals. And today, I'll speak more about healthcare. So I wanted to start with the diagram of when you're applying voice today, what's happening behind the scenes. It's usually a system, or what we call a pipeline. Brad showed that in the healthcare blueprint. And also Arun just presented 3 types of LLMs, a small one, a middle one, and a big one. But when you're deploying a voice agent today in that cascaded pipeline, as you call it, you can actually choose whatever LLM you want. You want a small, very efficient one because you don't have a lot of money to spend on every step and you want it to be quick, use a smaller one. You want to have a huge one, an ultra, and do really sophisticated reasoning when the voice is speaking, you can use a different one. So the cascaded option provides to you a very broad flexibility and customization options. But the way it works is it's really complicated. You need to handle audio and voice, either with WebRTC or WebSocket. So you have to shift the audio around the different components and then send it back. It's also about latency. And of course, when you need to process it in real time, it's all becoming very hard because you also have the network factor. All the data that needs to be stored and in the LLM, and to have context and to have history. And then you also have the interruption, voice activation detection. When is the user speaking? When is the bot is speaking? Am I just thinking for a minute and I don't want the bot to interrupt? So it's pretty complex systems. Here I don't even have RAG and I don't have guardrails and safeties, but it can be a pretty complex process. I still think that at least for the next few years, those deployments, and NVIDIA provides you with an ASR, LLM, TTS, but you can choose any model that you like. There's really good TTS models out there that providing even more flexibility and naturalness, and it really gives you the option to pick and choose. But then when you have that all together, that's ready for production. We also providing, there's a link on the top for a blueprint. It's very simple. It's a dev example, and you can take that code and deploy it. And it also has orchestration of all of the voice, and it's about 1 or 2 hours from taking that example and deploying and speaking to your own agent. But this is cascaded. Cascaded also have a lot of problems or issues because as you transfer voice or context between those steps, you're losing some things. You're losing the dynamics, you're losing the voice itself. In healthcare, it has an extra meaning because if I have issues with my voice and I'm going to a doctor and I have a sore throat, or I'm coughing, or I'm even, I don't know, I'm forgetting things and I'm umming, and you do want to have all of those things actually being heard by the voice agent. And that's where full duplex is actually coming to play.
Let's see, what do you want to talk about?
I'd love to hear a weather joke from you. Please
Sure,
share.
here's the joke. Why did the sun go to therapy? Because it had too many clouds.
That's a classic. I like it. So,
Thanks, I
what's
thought
your
you
favorite
would.
weather?
So how's your day going?
It's going well. Thanks for asking.
I'll explain after.
Having a little bit of a sore throat right now.
Oh no, that's no fun. Is it scratchy or more of a burning sensation?
Yeah, it's a little bit of sore throat and a slight burning sensation.
I see. That could be from overuse or maybe even a mild infection. Have you been talking a lot lately?
No, I haven't. I've been really quiet. I've been staying in bed all day.
That might be it. Sometimes lying down can cause mucus to pool in the throat. Try propping up your head with a few pillows.
Okay. And how do you know this?
I'm a doctor, so I'm trained to listen and provide medical advice.
Okay, I understand.
All right, so what you just saw, I hope it sounded more natural. What you just saw is actually two of our full duplex speech-to-speech models. One of them was announced at the keynote as an early access, and the other one is a research model that we released a couple of months ago. It was called Personaplex, and it's a fine-tuned version of Moshi from Qtai Labs. And on the one with the circle, the one that was like, who are you, and had this rusty voice, this is a Personaplex. It's super natural, and then we just added a few mixed voices. Those are not real voices. And the one on the left, on your left, the one that says, I'm a doctor, that's the Nemotron voice chat. And we prompted them. We just said, right, it's just role-playing. It's not really a doctor. And we just, one of them was a patient, and we said, well, you're just a patient, and the other one was a doctor. Those models are actually much more natural in the way that they converse. I hope you're able to understand that both of them are models. They're not humans. But the nice thing about those models is even as they mature, you will be able to even use that for practice. So if you have a practitioner, or if you want to train somebody to get those calls from patients, then one side can be that person who doesn't even know how to describe their illness, or if it's like a person like me whose English is their second language, and if you'll tell me to describe a scratch or a burning sensation, I also heard that from a different culture, you'll say, I have ants or I have spiders on my hand, and then we'll go get a pest expert. But no, it's actually a burning sensation or a cold sensation. So those are really interesting things that you can play with. And then the other side might even be that cascaded production use case that you have. So there's a lot of applications where now the voice is more natural. I don't know if you heard, it was like, it had this relief, and it was more emotional. So specifically in healthcare, that can be super helpful. And those are things you cannot get in the cascaded options, but well, maybe you can, it's super hard. So those models, by the way, this was created with Cursor, so I do encourage all of you to try vibe coding, it's super cool. And what I asked it to do is just take a static image, and show us what those models will do. So we need them to do tool calling. So it means when they're asking what's for breakfast, and that 1 sec is the model answering instantly, on the back end, it's actually performing a tool calling, and maybe there's a smarter LLM or a backbone that's doing all those calculations you're thinking, and then it comes back with the answer. It can be RAG, it can be a different system. And then it also handles interruption. So the model will know when you're barging in or when you're just taking your time. So those are really cool and hard problems to solve, and we're trying to squeeze them into a single model so it will be easier to deploy. You can take it to the edge. You can just have a much more natural conversation. So we're starting with an EA because it's hard, and those models, in order for them to be fast, we can just fit a small nano LLM backbone. So if you expect it to be super smart as your cascaded, not today. But you do have the option today then to choose the both of them and use the both of them as you like. So as for the voice chat, it's an early access. The team here, the SA and the DevRel, will help you get your hands on one. And it's still in evaluation because we do want to see exactly what's the first use case that you would like to apply such a model as we're maturing it. And they do provide a balance. So this is, again, artificial analysis, recent speech-to-speech leaderboard that was just updated. Very similar to what Arun was showing, just up and right. We're just changing the model names. But we are trying to deliver something that provides value. And the value here is a good balance between the intelligence that you see on the x-axis and then the emotions or the conversational naturalness, dynamics of the call. And it's really hard to measure that. A good benchmark today is full duplex bench, which provides really those pause and the interruptions, and that's on the y-axis. And just getting both of them at the same model is really hard. So it's really a balance. You can be very smart, but then you have a large LLM, or you can be very good in dynamics like Personaplex, but it will not be that intelligence. Yeah, so with that, last slide about how you can tune those models, both the speech-to-speech models and both the cascaded, to fit healthcare. If there are specific medical terms, if there's a doctor that's speaking in a specific way and you want to capture that, that's super hard in healthcare and a repeated problem with speech. So there's 3 layers. You can take an LLM and you can start adding 3 layers of fine-tuning. One of them is just term boosting. That's being supported at inference. You don't have to train or fine-tune that. The second level is a language model, or the language layer. So you can fine-tune and just add text. So whenever you're adding text, the probability of a next word that is closer to a medical terminology will pop up rather than just a regular word. So just add text, and the model will predict more the next word based on the specific jargon or terminology. And the last one is also acoustic. So if you're working in a very noisy environment, or there's fire mics or different background noises, you can always take that extra step. It's not super hard. You do need to have those skills of acoustic fine-tuning, but that's also applicable. And then once you're deploying it to production or to inference, it really depends on your use case. As I said, some of them require a bigger backbone of LLM. Some of them require something that's more lightweight. So do pick and choose. Now you have the option, and it's there. And then, of course, as it's happening, there's RAG and tool call. And you do need to understand exactly how are you reaching out with the wider system in order to fetch data or to retrieve it, or where all the questions were provided by the user, or does the bot needs to collect more questions before you move it forward in the next step. Yeah, so that's it. The last slide is actually just from today, just to show you that the ASR leaderboard is really shifting fast. If you want to deep dive into the advancement on ASR, go to Hugging Face leaderboard, go to artificial analysis, and see the advancement of proprietary models, bless you, and open models. And just recently, the leaderboard of the open source was really exciting. It's like every model is changing, but you can see that we're trying to support the ecosystem and just release more and more open ASR models that then are working on both the cascaded and are both supporting our speech-to-speech models. So thank you so much. Back to you.
Great. All right. So just a minute or two to wrap up. I mean, what you heard today is the technologies that you need to transform healthcare so that you can do your life's work is available now. Some in early access, some for download. What's so important is that we are restoring what it means to deliver healthcare for our clinicians. If you think about what's happened over the last 30 years, where we've asked doctors to key more stuff into computers, where we've asked nurses to make more phone calls and send faxes, and not be doing the nursing and not be doing the delivery of care. And now we're able to give that back so that doctors can be doctors, nurses can be nurses, clerks can be clerks, and we can transform healthcare for all. Thank you all for the phenomenal work that you are doing to transform this healthcare ecosystem. And I will turn it back now to Cedric to close out our session. Thank you so much, everybody.